Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits, Visakhapatnam. I welcome you all to my second lecture on the concept of time response of control system. In my previous lecture, I have discussed what is time response, what is steady state as well as transient state responses. I also discussed the various standard test inputs, that is step input, ramp input, parabolic input as well as impulse inputs. I have also defined what is steady state error and derived the expression for steady state error. And lastly, we have also seen the various factors on which this expression steady state error depends and its various effects. In today's lecture, we are going to see the various tutorials based on the theoretical concepts that we have seen in our last lecture. The first sum, it is given that the unity feedback system is characterized by open loop transfer function g of s is equal to 40 into s plus 2 by s into s plus 1 into s plus 4. We are asked to find the type of the system, all error coefficients, and error for ramp input with magnitude 4. So in the denominator, since the power of s is 1, so it indicates that there is one pole at origin. So therefore, the type of the system is 1. All error coefficients, we already defined what are the error coefficients Kp, Kv and Ka. So accordingly, since we know the expression of g of s into h of s, h of s is given as 1 as it is indicated in the system that it is a unity feedback system. So applying those formulas, and we'll try to find the values of Kp, Kv as well as Ka. The formula for Kp is limit s tends to 0 g of s into h of s. So on substituting s is equal to 0, the denominator becomes 0. So therefore Kp value will be infinity. Next, according to the definition, Kv is limit s tends to 0 s into g of s into h of s. So this will cancel the s term in the denominator. So when I substitute s is equal to 0, that will give me 40 into 2 divided by 1 into 4. So Kv value will be 20. And Ka value is limit s tends to 0 s square into g of s into h of s. So this will make the expression have an s term in the numerator. So upon substitution of s is equal to 0, will make the value of k as 0. And the last part of the question is we are asked to find what is the steady state error for ramp input with magnitude 4. So since it is a ramp input, we will utilize the value of Kv, and the expression of steady state error is nothing but A by Kv. Kv we have already obtained the value as 20, and the value of A, that is the magnitude, is given as 4. So steady state error ESS is 4 by 20, which will be 0.2. The second tutorial, it's given that the unity feedback system is characterized by open loop transfer function g of s is 10 into s plus 2 into s plus 4 divided by s into s plus 1 into s plus 5 into s plus 4. Determine Kp, Kv, Ka and steady state error if the input is r of t is 3 plus t plus t square. Here given that the the unity feedback system. So h of s value is 1. So we know the expressions for Kp, Kv and K. So according to the definition of Kp is limit s tends to 0 g of s into h of s. So because of this, there will be a s term in the denominator. So upon substitution of s is equal to 0, will give me the value of Kp as infinity. So next, according to the definition of Kv, it is limit s tends to 0, s into g of s into h of s. This will cancel the s term in the denominator. So upon substitution of s is equal to 0, which will give me 10 into 2 into 3 divided by 1 into 5 into 4. So that will give me the value of Kv as 3. And lastly, Ka according to the definition is limit s tends to 0, s square into g of s into h of s. So this will give the value of K as 0 obviously because there is an s term in the numerator, then upon the substitution of s is equal to 0 will make the value of K as 0. So now we know the values of Kp, Kv and K, and the input is also given as a sum of step, ramp and parabolic. So 3 is indicating step input, T is indicating ramp input, T square is indicating parabolic input. So we know that if it is step input, we utilize the error coefficient Kp. If the input is ramp, we utilize the error coefficient Kb. And if the input is parabola, we utilize the error coefficient K. So we know the expression also. We have derived the expressions of steady state error in our previous lecture. If it is step input, steady state error is A by 1 plus K. If it is ramp input, it is A by Kv. And if it is parabolic input, the steady state expression is A by K. Here A value in step input is given as 3. So A value is 3. So here in ramp input, the value of A is 1. But for parabolic input, the standard expression is A by 2 into T square. This is the standard notation of parabolic input. So according to that, A value is 2. So ESS steady state error will be 3 by 1 plus infinity since Kp value is infinity. Here 1 by 3 since Kv value we have obtained as 3, and 2 by 0 since Ka value is 0, which will lead to the steady state error value to be infinite. Third theorem, a unity feedback system is characterized by open loop transfer function g of s is equal to k1 into 2s plus 1 divided by s into 5s plus 1 into s plus 1 whole square. When the input is r of t is equal to 1 plus 60, determine the minimum value of k1 so that the steady state error is less than 0.1. So here the input is given as the sum of step input and ramp input. So it is sufficient if we find the values of Kp and Kv. So Kp, as we know, is limit s tends to 0 g of s into h of s. Since there is an s term in the denominator, the Kp value is infinity. And Kv is limit s tends to 0 s into g of s into h of s. This will cancel out the s term in the denominator, which will result in the value of kv to be equal to the constant k1. So since the input is given as sum of step and ramp, steady state error will be a by 1 plus kp plus a by kv. Kp value is infinity, so the first term will become 0 and the second term a value is 6 and kv value is k1. So the steady state error as a result will be 6 divided by k1. So we are asked to find what is the minimum value of k1 so that the steady state error is less than 0.1. So 6 by k1 is given, it is less than 0.1. So k1 value should be greater than 60 for the steady state error to be less than 0.1. So obviously the minimum value of k1 so that the steady state error is less than 0.1 is 60. The fourth tutorial, given that the unity feedback system is characterized by an open loop transfer function, g of s is k by s square into s plus 2 into s plus 3. We're asked to find the value of k if the steady state error is limited to 10, if the input is r of t is 1 plus 10t plus 20t square. Since the input is sum of step, ramp and parabolic, we need to find values of kp, kv and ka. So according to definition, kp is limit s tends to 0 g of s into h of s. Due to the presence of s squared term in the denominator, upon substitution of limit s tends to 0 will give me the value of kp to be infinity. Similarly, kv is limit s tends to 0 s into g of s into h of s. So one s term gets cancelled. Still there is another s term in the denominator which will give me the value of kv as infinity when I substitute limit s tends to 0. And lastly, ka is limit s tends to 0 s square into g of s into h of s. So this will cancel the s square term in the denominator. So upon applying the limit s tends to 0 will give me the value of ka as k by 6. So now the steady state error will be a by 1 plus kp because I have a step input as the first term where a value is 1. The second term, since it is 10t, it is ramp input. So therefore the steady state error will be a by kv. The third term is 20t square. It is parabolic input. So the steady state error will be a by k. So the first term a value is 1, the second term a value is 10, the third term the standard form is a by 2 into t square, isn't it? So for parabolic input, so the a value is 40 for parabolic input. So here, given that the steady state value is equal to 10, okay, so 1 divided by, so kp value is infinity, kv value is infinity, ka value is k by 6. So substituting the values of kp, kv and ka values and equating that to 10. So obviously these two terms will become 0. So which will give me the value of k as 24. The last tutorial, given that the unity feedback system is characterized by the closed loop transfer function C of s by R of s is ks plus b divided by s square plus as plus b. I was asked to find open loop transfer function g of s and show that the steady state error with unit ramp input is a minus k by b. So given the transfer function, that is the closed loop transfer function is represented by g of s by 1 plus g of s into h of s, because it is a unity feedback system and assuming that it is negative feedback system. So given that it is equal to ks plus b by s square plus as plus b. From this we have to find the value of open loop transfer function g of s. So I'll cross multiply this expression, and r of s is anyhow unit ramp input is given, so it is 1 by s square. So when I cross multiply, which will give me g of s into s square plus as plus b is equal to 1 plus g of s into h of s into ks plus b. So I'll multiply this expression, which will give me g of s into s square plus as plus b is equal to, so if I multiply, that will give me ks plus b plus g of s into ks plus b. Since it is unity feedback system, the value of h of s is 1. So if I take g of s as common, that will give me g of s is s square plus as plus b minus ks minus b is equal to ks plus b. So this two terms will get cancelled. So that will give me the open loop transfer function g of s as ks plus b divided by s square plus as plus minus ks. So if I take s common, then in the denominator I'll get s into s plus a minus k. Now since it is given ramp input, we need to find the value of kb. So according to definition, it is limit s tends to 0, s into g of s into h of s. So that will cancel the s term in denominator. So that will be, upon substitution of s is equal to 0, gives me b divided by a minus k. So steady state error is anyhow, we know that it is a by kb. Since it is unit ramp, it is 1 by kb. So the steady state error ESS will be a minus k by b. So hence we have proved that the steady state error with unit ramp input is a minus k by b. So this concludes my second lecture on the concept of time response on control system. Thank you.